Okay, let's continue. Well, just now we have already discussed this greedy solution that we want to trace down a number pyramid, and then we want to maximize the sum of all the values we have visited, right? Okay, so if we want to use this one, okay, so if we want to do a greedy solution, so we start from the 3 and then we check those two values. So and then we want to pick a greedy choice, right? So on the greedy choice, I'm gonna pick the 7. So I'm gonna say, okay, I want to pick this one. Okay, and after that, from 7 we check two values, 2 and 4, and we want to pick the higher one, so we pick this choice. Okay, and then from 4 we have 5 and 9, and then we want to pick a greedy choice, so we pick this one. Okay, so this is how we made the decision. Okay, and is this the highest possible sum of the numbers we can visit from top to the bottom? So in this case, we have a total of 23, and the answer is yes. So this greedy algorithm does give us the optimal solution only for this case. However, this algorithm, it doesn't guarantee to give us the right solution. So why? Because if you see, those are the values we have checked. Okay? This is the problem because we never bother to check the 6 here, 3 here, and 8 here, 8 there. Why? Because their parents are the smaller values. For example, we don't even have a chance to visit 6 because 4 is the smaller value compared with 7. And we don't have a chance to check 8 because 2, the parent 2, is a smaller value compared to 4, right? So how can I give you a sample that this algorithm doesn't give you the optimal solution? That's easy. Say if I change this 8 to 80, or if I change this 3 to 300, and then guess what? If we're staying with the greedy algorithm, and then we will still have the sum to be the 23, and then that is wrong. Okay, so the point I'm trying to make is, well, even though greedy algorithm is cool and it is fast and it is easy to design, it doesn't always give us the best solution or the optimal solution. Okay, so what's the time complexity of the algorithm? And it is O(n) because we only need to uh, trace down this pyramid once. However, this doesn't give us the right answer. Okay, so the next question is, what is the brute force way so that we can find the maximum of the sum of the trees from the top to the bottom? So if we want to do that in the brute force way, and then we have to exhaustively try all the different passes. Say, uh, so if we have a tree like this, and then there are two possible passes from the top down, right? So we go, oops, somehow it's not working. Okay, here. So well, in this case, if we only have a tree of two levels, and then we can either go this way or this way. And if we want to increase the tree level, and then, or if we want to increase the height of the pyramid, and then if we increase to this one, and then we have a total of 4 different traces. So we can go this way and this way, or this way, or this way or right and right. So in this case, we have a total of 4 different passes. And then if you want to increase the height by 1 again, and then we will have a total of 8 possible passes. And to make sure we find a trace from the top to the bottom, and then we have the maximum of the sum, we have to exhaustively visit all the possible nodes and then get the maximum of the sum, right? So that is a brute force way to solve this problem. So we can't go with the greedy algorithm because we can easily prove the greedy algorithm doesn't give us the right result. Okay, so why why have we spent so much time talking about this number pyramid and the greedy algorithm? Okay, this is the point. The point is, remember yesterday we talked about the card training algorithm, the algorithm we use to build the decision tree, right? So how do we do the decision tree building? Okay, so think about that. Let me create a new drawing canvas. So we start from the root. So this root should be the whole dataset. Okay, and then what do? We try all the possible splits, right? So we from the root, and then we can have the split 1, we can have the split 2, split 2, and then etc. And we can have a total of n splits. Okay, and then for each of the split, what do? So for each of the split, and then we will have the Gini 1 and then the Gini 2. And then we want to calculate the Gini 1, Gini 2, and then we want to have a weighted average. So eventually we want to have the weighted this is the weighted average of the Ginis for the split 1. And then for the split 2, that's the same thing. We want to have the Gini 1 and the Gini 2, and then eventually we have the weighted average again. And then after we have the weighted average of all the possible splits, how do we make the decision? So we are checking the weighted average, and then etc. So eventually we want to pick the lowest weighted average, and then that split will be the split we are gonna make. Okay, so what is that? That is indeed a greedy algorithm. So on each of the node, not just the root, but each of the node, what we are going to do is we just try all the possible splits, and then we make a greedy decision. The greedy decision is on the weighted average Gini after the split. Okay, so the card training algorithm itself is nothing but a greedy algorithm. So as we said, what's the problem of a greedy algorithm? The greedy algorithm doesn't guarantee to produce the optimal solution. So what does that mean in the decision tree? So for a decision tree, we make a greedy solution on the first split, and after the first split, we are going to have 2 nodes, right? And then on those 2 nodes, how bad are they when they want to split down? We don't know. We only guarantee that for the current split, that is a good split. And then for the further splits, we don't know. We only know the first split is a good split. And then in the further splits, and then if they are both terrible, we don't care because this is the greedy solution. So what's the point? The point is, with the greedy card training algorithm, we ain't gonna have an optimal decision tree. Our decision tree is built 100% on a greedy algorithm, and then if you're looking for a optimal, the perfect decision tree, well, we don't have that. Well, the card algorithm doesn't produce that for us. Okay, so this is the point I'm trying to make. The greedy algorithm and the card tree training algorithm. So to sum up, a greedy algorithm makes a greedy choice on each step, so it's easy to code, and then it's lower time complexity, but it doesn't always produce the perfect optimal solution. And the card training algorithm, the algorithm we use to build decision tree, that is also a greedy algorithm. This means we ain't gonna have an optimal decision tree. So the next part, how do we want to fix that? So to build an optimal tree is NP hard. So what is NP hard? So the short answer is, for the NP hard, it is not going to be solved in a polynomial time. So this is a computational heavy task to find a optimal tree. And actually, we don't have to find a optimal decision tree. Why? Because the next topic we are going to cover will be random forest. So we are going to continue our lecture in the next week. And so I think that's it. Okay, I will see you in the next video because there is a further question, a further task for you guys.